In section 4.3, we'll look at differentiation with exponential and logarithmic functions. So basically, we're going to take the information we learned from the past two sections, and now we're going to apply some calculus properties to that. We'll do the derivative. We'll look at the business calculus problems that have to do with exponential and logarithmic functions, and we'll look at the increasing, decreasing, called monotonicity, concavity, relative and absolute extrema, and inflection points, and all that sort of stuff. All right, the first thing you need to do in this section is perform the group activity. So basically, you just want to find this limit, and you want to do that by making a table of values. And the h's here go down to 0.001. If you are not confident about what the limit is based on this small of a number, you can continue to take smaller and smaller values of h as they go towards 0. So go ahead, and you can do this by yourself, or you can do this with your some people online with you, friends or whatever. Go ahead and do that. Pause the video, and then work this out and see if you get a number. It's a nice, easy number. Nothing too strange here. And go ahead and pause the video, and then pick it up after you perform the group activity. All right, let's go ahead and compute the derivative of e to the x. So to do this, we create a function, f of x, which is e to the x. And recall that whenever we started to find derivatives, we use the limit definition of derivative. So the derivative of e to the x, so f prime of x, is really the limit as h goes to 0 of f of x plus h minus f of x divided by h. So since f is e to the x, this is going to be the limit as h goes to 0 of e, and notice that the exponent on the e is the x, which corresponds to what you're inputting into the function. In this case, we're inputting x plus h. So this is e to the x plus h power minus, and now we have f of x, which is just e to the x, all divided by h. Now we have to simplify this. So we're going to have the limit as h goes to 0. The first thing I'm going to do is I'm going to split up this first term, this e to the x plus h power. Since the exponents are added, that means that they came from, let me write this in blue. That means that they came from e to the x times e to the h. And you can verify that by double checking and resimplifying that those terms on the left. You would get the sum there. Now I'm going to factor out e to the x. And that gives me e to the x times e to the h minus 1 over h. And notice that this term here, this e to the x, it's not, it doesn't have an h as a variable. It has e to the x. So it is considered to be a constant when we're dealing with a limit that involves h's. Since it's a constant, we can bring it out to the front. So we get e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And this is the limit that you did in the group work, and hopefully you discovered that that was equal to 1. It is in fact 1, and now we have e to the x. And there it is. What this tells us is that the derivative of the e to the x function is itself e to the x. And that's amazing. It's one of only two functions whose derivative is exactly equal to itself. Now, what does this really mean? Because this is very strange, right? The derivative of e to the x is e to the x. And why is that? Well, remember that a derivative is a rate of change. So what this is saying is that the rate of change in the e to the x function is equal to the y value of the function at each point. So whatever the y value is when you graph e to the x, that's actually the slope of the tangent line and the rate of change of that function at that point. That's a very special property, and that's sort of the impetus about where this e comes from. Recall that e is about 2.71, and so there was some number where it was exponential, where the rate of change was going to be equal to the y value, and boom, here it is. It's this number e with the function e to the x. Let's take a look at example number 1. Let's write what we know so far. So the derivative of e to the x is e to the x itself. And example number 1 says, let f of x equal x to the fourth times e to the x. Find the derivative of f. So we have to use the product rule. So f prime of x is equal to the derivative of the first, so it's 4x cubed times e to the x unchanged, plus the derivative of e to the x, which is e to the x, times the first one unchanged, x to the fourth. Now that is the derivative, but when we deal with these, we usually like to simplify it and write it in a better way. So the question is, what can you factor out from both terms here? Well, I can definitely take out e to the x, and I've got x cubed and x to the fourth, so I can take out x cubed. So I'm going to take out x cubed e to the x. On the left side, that leaves me with a 4. On the right side, it leaves me with an x. And then we'll just prettify this a little bit here and make it x plus 4. And there's your derivative. Example number 2 says, let y equal e to the 5x squared power. Find dy dx. So that's the derivative, and we need to use the chain rule here. So the rule says that the derivative of e to the x is e to the x. But now, since the exponent is a function, we're going to have to use the chain rule to tack on the extra derivative. So dy dx is going to be e to the 5x squared power times the derivative of what's in the exponent, which is 10x. And we just move that to the front. So we get 10x e to the 5x squared. So notice that the exponent stays the same, and then you multiply by the derivative of the exponent, right? So you get that extra multiplier from the chain rule. Example number 3, let p of t equal t times e to the negative 2t power. Find p prime of t. So we have a product rule here because we're going to multiply t times e to the negative 2x. And then, since the exponent is not just t, we're going to have to use the chain rule on that part as well. So let's see how this works out. So here's the first part, here's the second part. So the derivative is going to be the derivative of the first, which is just 1, times the second unchanged, e raised to the negative 2t, plus the derivative of e to the negative 2t, so that's e to the negative 2t power, times the derivative of the exponent, which is negative 2, times the first unchanged. And now we can simplify. I can take out e to the negative 2t. In the first spot, that leaves me with a 1. And in the second spot, it leaves me with negative 2t. Example number 4, let f of x equal x times e to the 2x. Find where f has horizontal tangent lines, where f is increasing and where f is decreasing. And while we're at it, let's go ahead and find the extrema of the function. So, all right, to find horizontal tangent lines and increasing and decreasing, you know that you're going to need the derivative. So let's take the derivative. And it's a product rule with a chain rule again. So the derivative of the first is 1 times the second unchanged, e raised to the 2x power, plus the derivative of e to the 2x power, so that's e to the 2x times 2 times the first unchanged. So this is e to the 2x plus 2x e to the 2x. Let's simplify by factoring out e to the 2x. And that leaves me with 1 plus 2x. Now to find where we have horizontal tangent lines, we take the derivative and set it equal to 0. So we're going to have e to the 2x times 1 plus 2x is equal to 0. This is already factored. That's why we go ahead and take that extra step to factor it out when we start with. So it's already ready to go. We're going to split up each factor and set each factor equal to 0, just like normal. And on the left side, I have e to the 2x is equal to 0. And if you'll recall from our properties of exponential functions, this equation has no solution. So you'll recall that the graph of b to the x is always positive. So the b in this case is e, so no problem. The x has been replaced by 2x, which you might worry a little bit about, but it's not really that big a deal. You're just doubling the exponent before you actually use it as an exponent. Sort of a contraction on the graph, but still, it's still just some exponent with a base that's a legitimate base, e. So it's still going to be positive. Since it's positive, it can never be equal to 0. So this has no solution. And that's going to be a repeating theme throughout this. A base raised to an exponential power can never be negative unless there's something else going on, right? But just your standard old base to a power, that can never be equal to 0. So you get no solution from that. Over here on the right side, we get x is equal to negative 1/2. So this is our only critical value. And now we want to do a sign chart. And also, since this is the only critical value, you know, we can find an absolute max or min, but also this was the horizontal tangent line position. Just to make sure that's clear. All right, let's do the derivative sign chart. So we have negative 1/2. That was a 0. And now my derivative was e to the 2x times 1 plus 2x. And we want to determine the sign at some test point. So if I test here at 0, for example, I can plug in 0, and we get e to the 2 times 0 times 1 plus 2 times 0. Well, e to any power is always positive, so I don't even have to worry about that in many of these cases. And then here we have 1 plus 2 times 0, which is positive. So this is positive. So it's positive on this side. The multiplicity on the root that was x equals negative 1/2 was odd. Was odd. So this is a negative because it changes sign. Now we can write the statement. So f is increasing on negative 1/2 to infinity. F is decreasing on negative infinity to negative 1/2. And f has a, we can start off by saying it's a relative minimum, right? Because it's decreasing followed by increasing at x equal negative 1/2. And it's only a relative minimum at this point because it's decreasing followed by increasing. The other condition that I need to turn this into a absolute minimum is knowing that the function is continuous. And the function was f of x is equal to x times e to the 2x. Well, if you have a function that is y equals x, that's continuous because that's a line. And if you have a function that is e to the 2x, that's an exponential function, that's continuous. And the product of two continuous functions is continuous itself. So this does, in fact, become an absolute minimum. Now the value of that absolute minimum is yet to be seen. So let's plug it into the original function. And that would be negative 1/2 times e raised to the 2 times negative 1/2. That's equal to negative 1/2 times, the 2's cancel, and that leaves me with an exponent of negative 1. But e to the negative 1 is 1 over e. And so this is negative 1 over 2e. And that's your absolute minimum value. Let's take a look at the rest of the derivatives that we need to learn for this section, and these are ones that you do need to memorize. So we already have the first one. The derivative of e to the x is equal to e to the x. And then down below, we have the derivative of b to the x. So this is b, any b that would be legitimate to work here. So this is b greater than 0 and not equal to 1. And that is b to the x times the natural log of b. So a lot of mistakes that I see on exams and stuff is students put natural log of x. It's actually the natural log of b, the base. And this is a number because b is a number, the natural log of b is a number. And all this is doing is it is scaling the regular exponential graph that you're starting with. So all exponential graphs have a rate of change based on their y-coordinate that is some multiple of that y number. And the question is, what is that multiple? Well, it turns out to be the natural log of the base itself. So don't forget, natural log of b is a scalar multiplier by that. All right, let's take a look at the logs. The derivative of the natural log function is 1 over x. And then the derivative of log in base b of x is 1 over x times the natural log of b. Again, the same criteria for the b applies, and the same cautionary warning about this being the natural log of b, the base, applies. I see a lot of people put x natural log of x in the denominator, and it is x times the natural log of b. All right, let's use those to solve some problems. Example number 5. Let f of x equal 2 to the x power plus the natural log of x minus log base 7 of x. Find the derivative. So we're just going to use the other 3 rules that we have here. So f prime of x is equal to, the derivative of 2 to the x is 2 to the x times the natural log of the base, which is 2. Plus the derivative of natural log of x is just 1 over x. It's just always true. And finally, the derivative of log base 7 of x is 1 over x times the natural log of the base, which is 7. All right, so there we have that. Let me provide you with one other side note to this as well. You may have noticed that whenever you take the derivative of x to the n, just the regular power rule, you get n times x to the n minus 1. So for example, if you take the derivative of x to the 5th, you get something with x to the 4th. It's 5x to the 4th. And so this exponent goes down by 1 to produce this. So the question is, what should you have gotten in order to get x to the negative 1? Well, by the power rule, it should have been x to the 0, because 0 minus 1 is negative 1. But that doesn't make any sense because x to the 0 is just 1, and the derivative of a constant is always 0. So up until now, there was no way to get a derivative that had x to the negative 1 power, which is, if you rewrite it, 1 over x. Well, now we know where that gap is and where it gets filled. It gets filled in by the natural log function. So for all the polynomials where x is not equal to negative 1, there is another polynomial that you can take the derivative of to produce that. And actually even x to any other real number as well. But if the exponent is negative 1, then what do you take the derivative of to produce that? The answer is the natural log function. So that fills in sort of this missing piece of derivatives with powers and things. Let's move on now to a little proof here. Example number 6. Show that the derivative of e to the x is equal to e to the x is a special case of the general formula for the derivative of b to the x equals b to the x natural log of b rule. All right, so this sort of shows that e to the x really is sort of the special case that works out the nicest way possible. So I'm going to take the derivative of v to the x, but I'm not going to use the fact that it is e to the x already. I'm going to ignore that for a moment. I'm instead going to use the general rule where it's a base. It's just some base. So here we have e. I'm using this rule right here. This is going to be e to the x times the natural log of the base. But the base itself is e. Now the question is, what's the natural log of e? Well, we've done this one before. The natural log of e is 1. And so then you do get e to the x, and it just simplifies straight on out of there. So that's the speciality here, right? All the derivatives of the exponents are multiples of the exponential function itself. So is there one that is a multiple one time itself? That's sort of the basic one. And the answer is yes, it's the e to the x one. So that's why this one is so special. Example number 7. Let g of w equal log base 3 of w squared plus 1. Find dg dw. So dg dw is equal to, and we got to use the chain rule on this. So it's going to be 1 divided by the argument of the log. That's what you take the log of. W squared plus 1 times the natural log of 3. Now that just completes the derivative of the outer function, which is log base 3. Now, by the chain rule, we have to take the derivative of the inside part, which is w squared plus 1. And the derivative of w squared plus 1 is 2w. And so we just rewrite this as 2w over w squared plus 1 times the natural log of 3. Let's look at a little harder example with example number 8. Let f of x equal 3x squared minus the natural log of 2x, all of that raised to the 5th power. So we're going to use multiple chain rules on this one. And the outer derivative piece is going to be a power rule. So we have everything raised to the 5 power. So we're going to bring the 5 down. Inside stays the same. Oops. Lower the power by 1 times the derivative of the inside. The derivative of the inside is equal to 6x minus the derivative of the natural log function. That would be 1 over 2x, except that now the natural log function has an inside with itself. And so you use another chain rule in this piece right here, and the derivative of 2x is just 2. And that's the derivative. We have to do a little simplifying here, but not much. The only thing that happens is that this 2 and that 2 cancel. So this is 5 times 3x squared minus the natural log of 2x to the 4th times 6x minus 1 over x. Example number 9. The price demand function for selling chocolate candies is P of x is equal to 3.50 minus x to the 1/3 power times the natural log of x, where x is in thousands of candies and it ranges between 0 and 6. Find the revenue and marginal revenue functions. So revenue function is equal to x times P of x. So this would be x times 350 minus x to the 1/3 natural log of x, which is 350x minus, now this x distributes to both of these. It can't get inside of the x with the natural log, but it can simplify with the x to the 1/3. And so that's going to be x to the 4/3 power times the natural log of x, because you add the exponents. The exponent on the outside x is 1. 1 plus 1/3 is 4/3. Now, to find the marginal revenue function, you just take the derivative. So the derivative of 3.50x is 3.50 minus the derivative of the second piece is a product. So I'm going to have to use the product rule. So I'm going to take the derivative of the first. It's 4/3 x to the 1/3 power times the natural log of x unchanged plus the derivative of the natural log, which is 1 over x, times the first piece, x to the 4/3 power unchanged. And now we simplify. So this is 350 minus 4/3 x to the 1/3 natural log of x. And next we distribute the negative, and we want to simplify the 1 over x and x to the 4/3 power. So recall that this is still x to the 1 power in the bottom, and you subtract the exponents. 4/3 minus 1 is 1/3. That goes on the top, so it is x to the 1/3 power. And there's no need to factor that one because nothing will factor from all three parts. Next, it says use marginal analysis to determine the approximate revenue from selling an additional 1,000 candies over the expected 2,000 candies. So this is the approximate revenue that's additional revenue, right? So maybe I should have typed additional revenue, right? Because that's what marginal tells us. It doesn't tell us what the exact revenue is, but it tells us how much more we're going to get from making a change in our sales here. So the the 1,000 candies sort of tells us that delta x is equal to 1, which is exactly when we use marginal analysis. Because marginal analysis is a slope, and it's the rise over run, but the run is just 1. So that's why we can just use the slope itself. 2,000 candies means that the base number x is equal to 2. So we're going to do revenue prime, marginal revenue, evaluated at 2. So this is $3.50 minus 4/3 times 2 to the 1/3 power times the natural log of 2 minus 2 to the 1/3 power. Type that out, work that out in your calculator. You get 1.076, which it means it's an additional $1,076 in revenue. That's not exactly what the revenue is, but that tells us approximately what the additional amount of revenue we would get if we increased our production from 2,000 candies to 3,000 candies. And it's in thousands because X was in thousands. All right. Thanks for watching. See you next time.